Lecture is going to be looking at what we call significant figures. Significant figures is a way of controlling for the guess within certain numbers. So let's consider how we measure objects. Let's say we wanted to measure the size of the tree to the right. When we use something like a ruler, inevitably we're going to find that within that point there, we have a little bit of a guess going on. The marks on the ruler are indicating just enough information for us to get close, but not enough information to have an absolute accurate value. Significant figures allows us to control the amount of that guess within the values that we're reporting. So if I look at the example here for our tree, I know for absolute certain that the 2 is an accurate value. I know for an absolute certain that the 4 is an accurate value. However, the value that is the 5 is going to be the value that represents a guess. We know it's someplace between the 4 and the 5 marks on the ruler, but we're not absolutely certain where that value falls, and so we can put a guess value in there. The last number when we're doing a measurement is always going to be a guess. Now, significant figures helps us minimize the impact of guessing on the actual mathematical use of those numbers. Consider values like this, 54.634 being added to 3.2. If we were not to evaluate the system for guesses, we'd get a value like this, 57.834. However, the 4 here in our first number and the 2 in our second number are both guess values. And that means that both the 8 and the 4 in our final answer are also guesses. That's a lot of uncertainty within that value. And so what we want to do is minimize the amount of uncertainty in the value, even if that means we're less accurate in the number we are reporting. So when we're looking at the rules for addition and subtraction, what we're going to do is always complete the addition as you always have. And now we're going to evaluate the answer for how many significant figures the value has. When we're doing addition and subtraction, that value is going to be rounding to the first common decimal place for both of the values. And so if we look at the system here, the 450 does not have any decimal places, and so we cannot include any within our answer. And so when we round our final answer up or down, we're going to get that to a whole number value, 524. Here's another example. Again, we do the math as we had been doing before, and now we're going to round to the common decimal place, and be that 100th position, 24.34 being our final answer. Here again, addition, we do our addition as we would, and again, we're rounding to our common decimal place. In this case, that results in a change of the value to 60.9. Again, we're still indicating that the value here is our uncertain value. Again, 8004.98 minus 3. That 3 has the uncertainty in it, and it has no decimal places following it, and so our answer cannot have any decimal places, and so we're required to round that value. Now, this is where, cognitively speaking, we start to find a little dissonance. We're starting to get uncomfortable with doing systems like this, because for most of us, we know that 8004 minus 3 should get us closer to 8001. The decimal places here have some uncertainty. The decimal places here have absolutely nothing. And so, again, there's a little bit of push in here to be as accurate as possible. Now, to determine the number of sig figs within a specific value, there's a couple of little simple rules that you're going to have to follow. And I think about them within the context of the Pacific and Atlantic Ocean. If you're familiar with American geography, we know that the Pacific Ocean is on the left side of the country and the Atlantic Ocean is on the right side of the country. If there is a decimal point present within the number we are evaluating, the present decimal place indicates that we are going to start counting the significant figures from the left side of the periodic table. If the decimal point is absent from our value, we're going to start counting from the right side of the value. We start counting with the first non-zero number. And so if we're evaluating the option here, 1.0450, there is a decimal point present, and so we're going to start counting from our left-hand side. The first non-zero number is our 1, and so I'm going to count all of the numbers after that. 1, 2, 3, 4, 5 digits are significant figures. Here's another one. Note how there is no decimal place, and so we're going to start counting from the right-hand side. We're going to skip the first zeros, and we start counting with our non-zero answer. And so we have 3 sig figs in this value. Decimal place is present, therefore we count from the left-hand side. We start with our first non-zero number being the 9, and we get to 4 significant figures. Now, when we're multiplying and dividing, the number of significant figures will become much more relevant. We're going to round our answers to the fewest number of significant figures of the numbers that we are using for the multiplication or division. And so in our example here, 48.3 times 2, 48.3 has 3 significant figures, 42 has 1 significant figure, and so our answer can only have 1 significant figure. We're going to round the 96.6 so that we only have 1 significant figure. Again, because I am not including a decimal place here, I start counting from the right-hand side, skip the zeros. The 1 is our only significant figure. Another example, 630 times 2. The 630 has 3 significant figures. The 2 has 1. Our answer can only have 1. We round our 1260 down to 1,000. 500 times 5.4. Again, we're going to do our multiplication and now evaluate both of the numbers we used for the number of significant figures. 500 has no decimal place, so we start counting from the right-hand side. We're skipping our zeros. It has 1 significant figure. 5.4 has a decimal place, so we're counting from the left-hand side. This counts, and so it has 2 significant figures. Our answer can only have as many significant figures as the fewest number of significant figures, and so we're going to have to round this value up to 3,000. Again, this has only 1 significant figure because there is no decimal place, so we start counting from the right-hand side. We skip our zeros, and this is our only significant figure. 89.3 divided by 54. Again, we're going to complete our division. And now we're going to round our answer to the value that has the fewest significant figures. Again, our top number, 3, our bottom number, 2. And so our answer can only have 2 significant figures. We're going to round the 1.6537 up to 1.7. 82,342 divided by 5. Again, 5 sig figs, 1 sig fig. Our answer can only have 1 significant figure, and so our final answer becomes 20,000. I know it may feel odd to do as significant of a rounding job as what we are displaying here. However, it's important to note that that 5 is fairly valued within a guess, that this is not a super accurate measurement. And so because of that, we really can't say with any certainty what the actual value would be. To respect the amount of a guess in that system, we're going to display it as a guess. Here, saying that this value is a guess, as is almost all of these.